Hi everyone, I'm Michael Kaneski, and this is my PhD thesis video. My work is about the Droplet Search algorithm for kernel scheduling. To understand my work better, we needed to know the definition of the kernel search space problem. But first of all, what is a kernel? Kernel can be a code or a snippet of code like matrix multiplication. Or it can be a complex model, such as a convolution network from Onyx model, PyTorch, TensorFlow, and etc. Search space is a set of possible candidate solutions that could be considered in solving a particular problem. In this work, the problem is to find the best parameter which can speed up the kernel. Kernel scheduler are made up of a set of kernels with different configurations and parameters. And these kernels have a connection, which is based on a neighborhood function. Another important concept is about the of local minima. The figure on the right shows an example of a point at which we have a convex neighborhood around the local minima. Of course, a local minimum might be a global minimum if you don't know all the space. The global minimum point is the minimum of all points in the space. In the figure alongside, point 7 is a local minimum point, and point 8 is a global minimum point. Thus, a search space can be defined by the same set of kernel, but different neighborhood functions. For example, in this figure, we have three local minima, the point 2, 4, and 6, and one global minima, the point 8. While the second one has only one local minima and one global minima. And the last one, we only have one global minima. So depending on which neighborhood function we are, the problem of finding a global minima maybe become easier to solve. To illustrate an example of kernel search space, suppose we have a matrix multiplication kernel, and in the purple, we are applying two distinct optimizations on the kernel, unrolling and vectorization. The x and y axis are the optimization parameters, and the z axis would be the execution time. When we run it for different parameters, we form a search surface. And each of the red points would be a candidate to be the next point to be chosen. But the search space is not limited to just a single surface. Different types of search space can be yield different results. And given a space, the challenge is to find the best parameter that will result in the best solution. To solve this, we needed to understand what auto-tuning is. Auto-tuning is the process of automatically find the configuration parameters to optimize the performance models on specific hardware. The traditional auto-tuning is very simple. You get your kernel and the compiler optimize it. And in the end, you have your code optimized on the same architecture. Example for traditional auto-tuning can be GCC or Crank. And when we compare between traditional and the modern auto-tuning, the most difference between them is the modern auto-tuning process is for specific domains like neural networks, while the traditional is for general purpose. Also, the modern autotuning can generate a code for several devices, while traditional focus on architecture. When we think in a modern autotuning, today, TVM or Tensor Virtual Machine, it is the first one that comes to my mind. TVM is an open source deep learning compiler stack. Currently, it has three auto-tuning, AutoTVM, AutoScheduler, and MetaScheduler. In this work, we will focus on the two first auto-tunings. This is because the third one is in development yet. This work has a lot of motivations. I will have specific ones. The first one is about the performance bottleneck in the kernel. The growing complexity of these models creates a problem, together with the increased scale of the datasets, which has brought the issue of computational performance to the forefront. Identify optimal parameters for a kernel makes it feasible to address energy consumption concerns as well. And neural network models spend energy is not avoidable, given that execution time and energy consumptions affect the outcome. And recent work shows that there is a strong correlation between energy efficiency and speed. Optimizing kernels execution directly impacts overall model performance. Given the user nature of these operations in neural networks and other machine learning algorithms. However, finding the best parameters that optimize the kernel is a challenge. Our inspiration is motivated by belief that Droplet Search can offer a new and practical solution to this problem. We want to work on optimizing kernel scheduling and increasing the efficiency of machine learning models in several applications. Double search is a gradient descent-based algorithm, which it is based on a Doppler expectation philosophy. Doppler expectation is not a theorem because it is easy to prove the contrary. Doppler expectation is a hypothesis. The hypothesis that Doppler holds is the downhill path. A downhill path is a contiguous descending chain, the original kernel to the optimal kernel. So here we have an example that Doppler's expectations holds. The algorithm can find the best solution. In this figure, we have an example which Doppler's expectation doesn't hold. Because V3 in the convex region 1 is a local minima. Another important about the hypothesis is the neighborhood set doesn't increase so much. So we would like to design neighborhood functions that produce small immediate neighborhood sets. The pseudocode of the Doppler is short and simple. The code is only 17 lines. The origin starts in the canonical kernel. The visitor variable focuses on not allowing a repeat of the kernel parameter. The neighborhoods function is responsible for collecting the neighborhoods kernel using gradient descent for this. Also, if your neighborhood sample is less than the number of threads, you use the speculation to fill the set with samples. Speculation is a process we created to reach a global minimum point faster. In this figure, point C is the best point given by neighbors. If we plot the vector in this direction, we will create the point S as the speculation space. So we can jump in the space to find a better solution. We apply synchronous parallelism in the process to measure the best candidate in the neighborhood. We created stop criteria using a confidence level of 5% to distinguish the runtime of samples. Now, Doppler doesn't stop when our neighborhood is invalid. It skips the invalid solutions and performs the next neighborhood. And finally, we return the best candidate if we don't have a better one or if the number of iterations is over. Using convergence algorithms such as Droplet Search can speed up the discovery of optimal solutions. This concept of convergence algorithm can be expanded to apply on several domains, include operator fusion and neural networks. We introduced a novel heuristic designed to reduce the search space associated with operator fusion in neural networks by decreasing the number of operators within a neural network. This heuristic decrease the search time required for convergence algorithms like Droplet Search. MST algorithms come from the term minimum spanning tree because it is always looking to get the cost which improve the fusion in a way to reduce the number of nodes. But before understanding their algorithm, let's understand how the computational graph works. A node in this graph means an operator, and which it has a unit cost of cycles. And the edge, in this case, is the memory bandwidth that it's needed to pass information from one node to another. And we have a limited amount of memory for input and output. Without this, for example, we could measure all nodes without constraints. So, for example, if you want to fuse in the node A and B, we can, because if you sum the inputs and outputs adds of the nodes A and B, we have 4 units of memory. But if you try to join nodes N and C, we will not be able to. Since the sum of the inputs and outputs adds is 7, and it is greater than 5. To compare with MST, I will use the DFS algorithm on the left side. Cadence uses DFS algorithm to choose the fusion. The reason for this is because it is fast and in general we have a good performance. The first choice of the methods will be the same because in both cases it is the best choice. Of course, resulting in the same solution. Now, the choice is different. The DFS algorithm will choose the new next node D. However, MST will choose the best combinations that will respect the capacity number. In this case, it will be the node C. If you try any other combination in this graph, you will not find another possible solutions without breaking the memory capacity limit. And we will have the reduction of the memory in 1 unit. I know example is simple, but note that the larger the graph, the greater the reduction cycles and memory in a narrow network. As a contribution to my work, we develop a space form as a coordinated and the kernel point have in an order, something that didn't exist in TVM before. We have added the use of parallelism to run neighbor kernels faster. We also created the speculation system to take advantage of the number of threads on the device and avoid possible local minima. And we created an algorithm that reduces the number of kernels executed in the search space. My work has 90 research questions, but in this video, I will focus on only 4 of them. The first one is responsible for evaluating how Doppler expectations holds in different architectures. The second one, we will discuss about the analytical cost model. The third one, we will measure the performance of the DP answer against the answer. And the last one, we measure the impact of fusion and 90 network models. The experiment which I will present in this work is in the architecture X6, ARM, and CUDA. For this experiment, we collect 19 Onyx models from Onyx Zoom GitHub. We select the first K solutions from the 10,000 sample. So for example, imagine that K is 50. So we get the first of 50 samples of the 10,000 samples from answer. and we get the best configuration in the subset of samples. Our networks range from small to larger and dense networks. For the first research question, we will measure the Doppler expectation. We can see for exit 6, Doppler search saves time to visit the neighbor, and they found the global optimal point for matrix multiplication. This happened in matrix multiplication kernel because of the use of L1 and L2 cache memory. When we're looking at the same kernel and CUDA platform, we find a global optimum solutions too. In this case, of course, because of the use of memory sharing. In research question 2, we focus on analytical models. Analytical cost models are systems of equations that predict the cost of a program given a model of the hardware. We evaluated Oliver's et al.'s cost model for single cache one, L1, and we can see that Droplet can hold global minimum point solutions in few steps. When you consider L1 and L2 cache memory, even on different tiles, we can see that the Droplet finds the global minimum. However, when they consider an equation generated by XNC compile from Canvas, the cost was generated by loop functions, and the coefficient C represented the cost of particular structures. W and 8 are the tile size. In this case, the Doppler cannot hold the hypothesis because we have several minimum points locations. Even so, double search stays very close to the optimal solutions in comparison with an exhaustive grid search. Although the doublet uses less than 1% of the space covered by an exhaustive grid search. Hajapa et al. Shows that models used to solve the tile size selection problem are represented by equations whose coefficients and domains are all positive quantities. These equations all represent the instance of the bidimensional tile size selection problem. For representing this model, I consider these parameter values. For example, I present two of these equations. You can note that these two equations are positive, and the operator expectation holds in all these analytical models. In similar analytical models, we can see that the functions are positive. The use of Droplet Search finds the global minimum for these equations too. Actually, all of these equations use only positive coefficients, thus yielding a convex surface. In our research, we identify that answer is a good aspiration to find a good scheduler. But we notice that the operator is a good exploitation algorithm. And this is create an idea to use answer as a start point and operate to optimize from this. We call this technique DP answer. Let's see how it performs against 10,000 samples of answer. On the y-axis, we have the execution time relative to 10,000 samples of answer. On the x-axis, we have the 90 benchmarks. If we choose only one sample and use DP answer to optimize it, we will have worse solutions than 10,000 samples of answer. But if you choose 50 samples, we already have solutions as good as answer produce. And we can see that as we increase the number of the samples, the results tend to get better and better. And when we reach the top of the 1,000 samples, our results start to stabilize. And performance gains don't get so much better. And let's look at the search time issue, how much better it was. So on the y-axis, we have the search time relative to 10,000 samples of answer. When we consider up to 50 samples, our results are still faster than running 10,000 answer samples. We start to see a small delay after 100 to 200 samples on DenseNet. And for 1,000 samples, we start to see that our solutions ends up being a bit slower than running all the 10,000 answer samples. And when we consider our architectures like x86, CUDA, and ARM, we can see with 200 samples is enough to get a better solutions in relation to answer with 10,000 samples for our architecture's measure. About research question 4, we measured the impact of the fusion in DSP. DSP means digital signal processor. It is a microprocessor chip. In this case, we have P6, a DSP from Cadence, which is aimed at visual processing. Again, we use the same 19 benchmarks. We have five approaches. The first is without fusion. The second is the method using DFS. The third one is our approach, NST. Fourth is about evolution algorithm, the same one that TVM uses. And the last one is backtrack. When we when we compare to without fusion, our approach has a reduction in the number of cycles that is comparable to the evolutionary algorithm. In numbers, we was 76% better than no fusion. We was 39% better than DFS. In relation to evolutionary algorithm, we have the same performance. In relation to backtrack, we was 14% better. And when we compare the search time, our solutions only has a small delay compared to the DFS, on average around 11%. In numbers, we had a delay in relation no fusion around 37%. In relation to DFS, we had a delay in 11%. In relation to evolutionary algorithm, we were 29% faster. And in comparison to backtrack, we were 4 times faster. Consider the geometric mean, MST was the best among the algorithms in terms of cycle performance and search time as well. We showed the Doppler expectation hypothesis can be healed. Also, in the case where the hypothesis cannot be used, Doppler had a good solution. Doppler is a good competitive algorithm against the other TVM algorithms. And since the version 0.13 of the TVM, Doppler is part of them. We have created a PR to TVM about the P-answer, and we already have a proof on the project. We are waiting for the merge to TVM in the future. This synergy between our heuristic and convergence algorithms like Droplet Search has the potential to speed up the optimization process, making it a contribution to the field of neural network optimization. During my PhD, I had the opportunity to work on three other projects, which gave me the basis for creating research questions and discussions. I also developed two not related papers, one on high-level synthesis and another one artifact evaluation. The first paper is the main contributions of this thesis. It introduced the Droplet Search, which was published on TACO Journal. The second paper shows a methodology to combine exportation via Droplet Search. We have submitted to tackle in this year. In the last paper, applies the concept of convergence algorithm to operate fusion and neural networks. Recently, we sent it to submission to conference. I would like to thank you for all support I received during my PhD. And special, I would like to thank you, Fernando, and my friends in the lab. I really enjoy being part of the lab during these 4 years. Thank you, guys. And I would like to thank you, Cadence, especially for Vanderson and Eric for the opportunity to work there. I really feel happy to be part of the team. Without Cadence support, I wouldn't have most of the results I have got today. So thank you so much. So thank you for everyone to watch me.